So this is the second thread of this class, of this unité d'enseignement. The first one last week, we started on linguistics, and the second one is on symbolic approaches. And the third one will be on machine learning. Now, what we will see in symbolic approaches will, in some cases, be very close to things we will see in linguistics, because linguistics and mathematics join each other in the case of syntax. Things we will see today have been invented, introduced by a linguist, even though they are used mainly in computer science. So here is a very general, a very global point of view of this problem. And this is a principle which can be applied to any discipline, any domain. And it's the basis of scientific school called structuralism. So structuralism was seeking for structure. It started with ethnology, with Levi-Strauss, and then moved to linguistics with Barthes, and then to psychoanalysis with Lacan, and to history with Foucault, and so on. The fundamental principle of structuralism is that we can describe a domain using two axes, the syntagmatic axis and the paradigmatic axis. We define elementary units in our domain. How do we define these units? They are defined in order to be compatible with the syntagmatic and paradigmatic axis. So the paradigmatic axis is, when I have a unit, can I replace this unit by some other unit? What are the units that can be put instead of this unit? So in my example, la fille mange la pomme, instead of fille, I can put other words. Fille, femme, meuf, dame, chenille, any feminine noun can be placed in that position. So when I change these elementary units, I'm moving in this axis, which is called paradigmatic, from the Greek paradigma, which means example. So these are examples. The syntagmatic axis is how we combine units. So you see different units. La fille mange la pomme are units, and they are combined by doing, as we saw last week, first articulation. Okay. And this principle has been applied in any possible discipline. So, for example, you have a book on fairy tales, on Russian fairy tales by Pop, and he says, in a fairy tale, I have specific structural elements. There is the king, the daughter of the king, the dragon, and the hero, and so on. So these are the elements, and I can change them, permute them, replace them. And then there is the syntagmatic axis. How do I combine these elements? With the king goes to the dragon, or the hero goes to the hero kills the dragon, or the dragon kills the hero, and so on. And so he described a large corpus of fairy tales using this method. Okay, so as you see here, to formalize a situation, we need to define our elementary units and some means to combine them so that we have both the paradigmatic and the syntagmatic axis. The first kind of formalization we will see are formal languages. And formal languages, we define elements. These elements we will call the alphabet of our system. We define a means to combine them, and combination will often be concatenation, but there may be other ways of combining. And we need a way to say among all combinations of the elements of our system, which ones are allowed by our situation. So we don't accept all combinations, we just want to keep some which are useful for our purpose. And here I have some examples like the display of a pocket calculator. You have elements which are symbols 0 to 9, plus, minus, times, and so on. Concatenation to combine them, and some combinations which are allowed, like this one, 5 plus 3, and others which are not allowed, like this one, 7 plus times 3. But the same methods applies to the study of DNA, to syntax in a natural language, to chess, and even an autonomous vehicle watching the road will detect elements. So the units will be a human, a tree, the road, a sign, another vehicle, and so on. And the combination will be how these are positioned relatively one to each other, and accepted situations will be the human is on the side of the road, and not accepted situation is the human is just in front of me. Okay, so even an autonomous vehicle will have to deal with formal languages for describing the perception of the world it has. The image it sees is interpreted into a language, and the syntax will tell the vehicle whether this situation is okay and it can continue moving, or whether this situation calls for an immediate stop. The method we will use is the one of formal languages, where the elementary units are called letters. The set of all elementary units is called alphabet. And the combination of these units, so the syntagmatic axis, is called a word. Now, as you can see here, I have placed parentheses around the word formal, just to remind you that even though in our examples we will really use letters, formal languages are applied to a large number of cases where the alphabet is not made of letters. So formal letters can be completely different things. So it can be people, it can be objects on an image, it can be parts of a DNA, and so on. So keep in mind that even though we speak about letters, alphabet, and word, we are in fact referring to very general notions, and this can be applied to any possible situation. Okay, now for our purpose, we will denote an alphabet by letters, concatenation either by a dot or by no symbol at all. These are words, AB, BB, AC, and so on. There is an empty word, which we write epsilon, and a language, so a formal language, will be a set of words. And do not confuse the word which has only one letter with the element of the alphabet. This is not at the same level. It's like sets. Okay, so words are sets but they have an order. So mathematically, formal language is a subset of the three monoid. What is a monoid? A monoid is a set with an associative binary operation. Associative in what sense? Well, whenever we don't need to put parentheses, we call this an associative operation. So this BBAC can be B applied to BA or BB applied to A, and so on. So parentheses are not needed. It's associative. And the identity element is the empty word, which is added to a language, which is not necessarily included in any language. Now, it's very easy to define what a formal language is. It's just a set of words. The difficulty is to describe these words, to have a means of saying these words belong to the language, these words do not belong to the language. If the language is finite, then we can describe it by giving all words. We call this an extensional description of the language. For example, here, this is a language. When the set is infinite or very large, then we use intentional methods. So notice here an S. This is not intention in the sense of I have the intention of doing something. It's intention as the opposite of extension. In extension, intention. And it means describing something by giving properties. So for example, when I say the language of all words over the alphabet AB that start by n letters A and are followed by an equal number of B, I am using natural language to describe a formal language, which is infinite because there is no boundary on n. And this is a perfectly adequate way of describing it for humans. So you understand exactly what I mean, and you can say, if I give you an arbitrary word, you can say, okay, it belongs to the language. No, it doesn't belong to the language. Now, how do we describe it to a machine? A very intelligent machine could eventually understand this description, where you see I'm putting the first word, second word, the third word, and with some intelligence, you can figure out what will follow. But this needs a very intelligent machine, and there can be ambiguities. So in what way can we intentionally describe a language to the machine? And this is exactly what Chomsky has introduced in the 50s. He introduced a mechanism called formal grammars. He was a linguist. He still is a linguist. He's still alive, very old, but still alive and active, especially in politics, in left-wing politics. And he was inspired, of course, by natural language, being a linguist. So he called this a grammar. The idea is that you have rules and you have a start symbol. You apply rules to the start symbol and you obtain intermediate expressions. At some point, you cannot go any further. You get a terminal expression, and this expression will be a word of the language. He was, of course, inspired by syntax, where you have the sentence. A sentence contains a group noun phrase and a verb phrase. The noun phrase contains an article and a noun, and potentially adjectives, and so on. Each time I say a sentence contains this, a noun phrase contains that, these are rules, so-called production rules. Now, before I give you an example, let me recapitulate. You have 4 kinds of objects. The first one is just your alphabet. These are called terminal symbols because you cannot apply rules to them anymore. You have reached the end. Then, and this is the big innovation with this method, you have non-terminal symbols, intermediate symbols. So in natural language syntax, non-terminal symbols will be, for example, noun phrases. When we say this part of the sentence is a noun phrase, then we introduce a new concept, which is intermediate between the sentence and the words. We have this intermediate group, which is called a noun phrase. So these are the non-terminal symbols. Then we have production rules. This is the most important in Chomsky grammars. And finally, we need a place to start. So we call this the start symbol. And in French, it's much more poetic. It's called axiome de départ. Production rules, an arbitrary production rule can be written like alpha gives omega. Now, we have a condition for a rule to be applicable. We need that alpha contains at least one non-terminal symbol, because if alpha contains only terminal symbols, then nothing can be done anymore. Then we have reached a word of the language. But if this alpha, which is a word, contains at least one non-terminal symbol, then we can apply a rule to this non-terminal and obtain something new. And since alpha contains at least one non-terminal symbol, we can write it like this: beta, which can be arbitrary, R, which is a non-terminal symbol, gamma, which is arbitrary. And so an arbitrary rule is written like this: beta R gamma 2 omega. Now, depending on conditions on this expression, you have many types of languages, many types of grammars. The most general case is type 0. There is no condition on beta R gamma omega. It can be arbitrary. Then we have context-sensitive grammars where you have a condition on omega. It is written beta psi gamma. So in fact, what you are doing is you are replacing A by psi in the presence of beta and gamma. Beta on left, gamma on the right. So we call this context-sensitive. Beta and gamma is the context, and this context remains the same. And of course, psi can also be an arbitrary word. Type 2 are context-free grammars, no context. This means that beta and gamma are empty. So these languages are very important, especially in natural language processing. And you see that they apply to a non-terminal without any context. So on the left, you have a non-terminal, a single non-terminal. On the right, something arbitrary. And finally, the simplest languages are called regular languages, and they are like context-free on the left. You apply the production rule to a non-terminal, and what you obtain is either a terminal or a terminal followed by a non-terminal, or a non-terminal followed by a terminal. And you have to choose between the last two. In the first case, we call it a left regular grammar. In the other case, a right regular grammar. And you cannot have both. So either you produce only terminals, or you produce terminals followed by non-terminals, or you produce only terminals preceded by non-terminals. So let's take an example. Here I've written my alphabet, my set of non-terminals. I have only one non-terminal called S. Here are my production rules, and this is my start symbol. So this is a grammar. What is the language recognized by this grammar? So we say that a word is recognized by a grammar if it can be obtained by applying successive productions to the start symbol. So you take the start symbol, you apply a production rule, you get a word, you apply again a production rule to this word, and so on. A series of production rules is called a derivation. So a word is recognized by a grammar if it can be derived from the start symbol. And this is the language recognized by the grammar. It's the set of words recognized by the grammar. And a word that is not recognized by the grammar, so no matter what productions you use, you can never obtain this word, does not belong to the language recognized by the grammar. Let us take this example here. What is the language recognized or generated, is another term we use. What is the language generated by this grammar? To find out, let us look at what we can do. So we necessarily start with S because S is our start symbol. From S, we can obtain either AS or B. If we obtain B, then we are finished because the word containing only B has no non-terminal, so we have to stop. If we obtain AS, then we can start again. And again, we can either use this rule, another AS, or that rule. So this means that to obtain any possible word of this language, we will first produce A's and at some time a B. And once we have produced the B, we are finished. So the language generated by this language is the language of words starting with 0, 1, or many A's and ending with a single B. So it can be B, but it can also be AB, AAB, AAAB, and so on. Now, question, are these two words recognized by the grammar? Yes, the first word is recognized. How do I prove it? I take S, I apply this rule once, I apply this rule twice, and then I apply this rule, and I get AAB. Is this word recognized by the grammar? No. Why? Because to get a B, I need the second rule, And the second rule produces a single B. So there is no way to get another B. So I can prove it by saying that whenever I apply a rule, I have only one S in my word. And when I have a single S, I can produce a single B. Okay, so this word does not belong to the language. Now, remember these four types of languages. These are the simplest ones, and these are a bit more complex. In natural languages, we will use those two, so context-free and regular. Let us start with regular languages. Regular languages can be described, of course, by formal grammars, as we have seen. This is the case of all languages. But we have two additional tools to describe regular languages. They are finite state automata and regular expressions. And today we will talk a lot about these two tools. Now, there is no regular expression tool for context-free languages, but there is an extension of finite state automata for context-free languages called push-down automata. And we will see an example of push-down automata as well. Now, between regular and context-free languages, you may think that context-free are more difficult to obtain. That's not true. Here you have a typical example of a context-free language. AN, BN, with the same N. So what happens with this specific language? It is not regular. Why is it not regular? Because when I start adding A's, I have no means of counting how many A's I have added. Remember that in a regular language, I can add terminals only either on the left or either on the right, but not both. So to get an A5, B5, for example, I will add 5 times A on the left. How do I know that I have to add 5 B's to the right? I can't. Either I use very general rules allowing me to add A's and B's on the left and on the right arbitrarily. In that case, I will get, of course, all words A and Bn, but I will also get words with unequal A and B parts. Or if I write very strict rules, then there is no means of knowing when I add the B's how many A's I have added. So this is impossible. I can get these languages with this language, with this production rule. But this production rule is not one of a regular language because it adds terminals on both sides. So let us take the first tool, regular expressions. So this is something you have already used, perhaps not knowing that you are using it, because they are implemented in text editors and word processors for searching and replacing operations. A regular expression is a formalism using elements of your alphabet, so letters, and some special symbols. The special symbols are quantifiers, disjunction, parentheses, and maybe some other auxiliary symbols. So this means that when you write a word, you have only terminals. When you write a regular expression, you have terminals and some special symbols. Now, what happens if you want these symbols to be part of your word? In that case, you have to protect them. We will see how it works. Now, example. This language, which I have described here, can be represented by this regular expression. So it's A with a quantifier saying 0, 1 or more times, and a single B. So when I write a terminal without quantifier, I mean exactly once. Otherwise, the quantifier says how many times the preceding symbol or group of symbols, if I use parentheses, can appear in a word. So for example, if I want the three words pure, pire, por, I can write P between parentheses, U or I or O, R, E. Now, let me take this example. Does this expression represent this language? Pur, mur, pur, mur. If I'm asking this question, of course, it is because there is a trap. What is the trap? It's the fact that the language represented by this regular expression contains these words, okay, but it also contains many other words. For example, it contains P, U accent circonflexe, R. So pur with an accent circonflexe, or mur with an accent circonflexe. So it contains other words than these. So the difficulty when writing regular expressions or grammars or any formalism, difficulty is not to represent the words we need, but also to keep only those words. So to avoid having a super language, a language containing the words we want plus other words we don't need. In computing, there is a syntax called Posix for regular expressions, which gives us many gadgets. So here I have only the basics, what has been defined from the beginning in the 60s, and Posix, which is used by programming languages, introduced many gadgets. In Posix, the alphabet is Unicode. And you have ways of defining some specific characters like carriage return, new line, tab, an arbitrary Unicode character in the range between 0 and FFFF, and an arbitrary Unicode character above this. For example, this one, which has 5 hexadecimal digits and is the smiley with glasses. So the backslash is used to protect characters. Protect characters, for example, the parenthesis is a special character. It allows grouping. If I want a parenthesis in my word and not in my regular expression, but really in the language, I would use a backslash to protect. So the backslash will protect characters and also will define some special characters. Now, I can obtain ranges or sets of characters using brackets. bracket 0 to 9 means from 0 to 9, inclusive. Here we have brackets which are special characters and also the dash. Dash is the range character. If you want a dash in your set, then put it as the last character. Otherwise, it's a special character. Here I get capital letters from A to Z, but with the exception of F, and lowercase characters from A to K. And here, when I put a hat right after the opening bracket, it means the complementary of what follows. So this means any character which is not a lowercase or uppercase Latin letter. The period means any character besides carriage return and new line. So this is very useful when you have text data with lines. So you want an entire line. And this here I have protected the brackets. I have the parentheses and the braces when we are inside brackets do not need to be protected. It's automatic, but brackets need to be protected. Quantifiers, you have the question mark, 0, 1, star, 0, 1 or many times, plus 1 or many times. We will see all that in the lab, so don't memorize it now. You will have more opportunities a bit later. Now, what need to be understood is that we have two kinds of quantifiers: greedy quantifiers and non-greedy. The difference is that a greedy quantifier will recognize the longest possible string. So if I have a word with 25 A's and a B, and a regular expression A plus B, it won't recognize just the last A before the B or just a few A's before B. It will take the longest possible string, 25A, and then the B. If I put a question mark after the quantifier, I'm getting non-greedy quantifiers. Non-greedy means take the shortest possible string. And this makes sense when I have boundaries. So for example, if I take this without the question mark, a search pattern like this would recognize a B tag followed by a very long string and ending with a /B tag. But inside the string, I could also have other tags, other B tags, because I'm taking the longest possible string. Putting the question mark, I get the shortest possible string, starting with a B tag and ending with a /B tag. And this is usually what I want. And we can also use the disjunction operator, for example, here, mon, ma, frère, sœur, adoré, question mark applied to E. We can use the backslash followed by a number to duplicate parts of the expression. So for example, here I have parentheses containing blah or blee. By putting a \1, I mean, again, the contents of the first group of parentheses. Here I have two groups of parentheses. This is the contents of the second one, and this is the contents of the first one. So for example, if I take the name of the ABA group, I can recognize A, a B, and then a B, same thing as here, and an A, same thing as there, and the word ABA belongs to the language defined by this regular expression. And here I have a few gadgets. For example, if you have a group, but you don't want this group to be memorized and used with \1, \2, and so on, you start the group with parentheses, question mark, colon. And you have the possibility of defining look behinds and look aheads. Look behind is I'm searching for ABC only if it's preceded by DEF. And the look ahead is I'm searching for ABC only if it's followed by DEF. Now, you may wonder why use such a kind of complicated expression. We will see in Python that you can search for several occurrences of words in a string. And if I put DEF simply without this notation, then I will capture, no, this example is better. If I put here DEF without parentheses, then I will capture ABCDEF. This means that the next word found by my Python code will not contain DEF because DEF is already taken by that expression. By using this notation, I find ABC and DEF is available for the next search, the next automatic search. Okay. Now, let us move to the second tool, finite state automata. As I said, regular expressions in finite state automata are tools for describing regular languages. And it has been proven that they are equivalent. So if you take formal regular grammars or regular expressions or finite state automata, they describe the same languages. If one language can be described by one of these tools, it can be described by another one. If a language cannot be described by one of these tools, then it cannot be described by the other one. They are strictly equivalent. How does a finite state automaton work? We have two tools, two ingredients. We have states and transitions. States are conditions, situations, and transitions are operations of moving, of changing state, going from one state to another. So you take a door, it's either open or closed. If you open it, then it changes state. It becomes an open door. And then if you close it, you'll return to the previous state of closed door. How do we change states? By transitions. How do we fire transitions? Do we execute? Do we do transitions? They are triggered by letters of the alphabet of the language. So whenever you read a letter belonging to a word, you have to consider whether you are changing state or maybe staying at the same state. So letters are triggers to change states. Now, you have ordinary states, and then you have two kinds of states which are more important, initial and terminal. Initial states are those where you can start. You can say, I'm here. It's an initial state, so I decide I'm here. And my first letter will allow me to move to some other state. Terminal states are those that imply recognition of a word. When you are moving inside an automaton and your word which you are reading ends, then you are at some state. If this state is a terminal state, then the word belongs to the language described by the finite state automaton. If the state you have reached is not terminal, then the word does not belong to the language. So this is the idea. This is how finite state automata recognize languages. So I take again the same language, A's followed by a single B, and here is a finite state automaton. It's finite because it has only two states. This one is an initial state. We see it by this arrow, which enters, which comes out of nowhere. So this means one is an initial state. Every time there is an A, I stay in the same state. And when there is a B, I move to a second state, and this state is a terminal one. So you see, to get B, I just start with 1, write a B, I'm in 2. For writing AAAB, I start with 1, I write an A, again 1, another A, again 1, another A, again 1, and a B, and I am in state 2. Now, question, does this automaton recognize only the words of this language? Or does it recognize other words? Well, what is missing here is what happens if after the B, I have another letter. We know that in this language, all letters end with a B. So if I add another letter after my B, no matter what letter, then the word should not be recognized. But here, this automaton does not give me this information. So I need another information, but what happens if after the B, I still have other letters? So our first idea would be to write this. So if other A's and B's appear, stay in the same state. But that's not good, because it means that I can add other letters, AAB, AB, AB, and I'm still in a terminal state, which means that the word is recognized, and I don't want to recognize this word. So a better idea is to introduce another state, state number 3, and say, if after this unique B, there are other letters, then I enter the state 3 and I stay inside the state 3. And this state 3 is not terminal. So if after your B, your unique B, you add other letters, it's finished. You will never get a terminal state again. So this automaton on the bottom of the slide is really the automaton describing this language. So this language has been chosen to show you that if you have only two states, you get a super language of this one. And if you want exactly this language, then you need an additional state. So you see how important it is to put restrictions. Now, a deterministic finite state automaton is an automaton where you can make no human choices. You can never say, now do I go to this state or to that state? Here is an example of a non-deterministic finite state automaton. You see that from state 1, you can leave with letter A in two possible ways. You can either stay in the same state or go to state 2. So both are possible. And when the machine reads an A, it has to choose whether it stays or whether it goes. This is also a finite state automaton that recognizes a language. It works. It recognizes the same language as this one, in fact. But it also recognizes other words. Okay, now being deterministic means we have only a single initial state. So no possible choice. We can only start from a given state. And for each letter and each state, we can have only a single transition. So no choice is possible. Fortunately, we can go from non-deterministic to deterministic finite state automata. There exists an algorithm called the Determinization Algorithm. So for every non-deterministic automaton, you can get at least one deterministic one. And when I say converting from non-deterministic to deterministic, I mean equivalent. So recognizing exactly the same language. Now, when I draw an automaton like this, it looks quite mysterious. You may ask, you may wonder what is the information hidden here. And in fact, the information that entirely describes an automaton is very simple. It is a single table. It's called the table of transitions. Rows of this table are states, columns are letters, and for each state and each letter, you just say, when I am on this state and I get this letter, then I go to that state. And that's all. Initial states are marked by an incoming arrow. Terminal states are marked by an underline. And this describes exactly this automaton. So you see our graphic description is mainly for humans, and the machine only knows the table of transitions. And of course, this table of transitions, if your automaton is deterministic, you will have only one number here in every cell. If it's non-deterministic, you may have several state identifiers in a single cell. Now, imagine we want to do more than just regular languages. Then we need a more powerful structure, and we can extend automata from finite state to push down automata to describe arbitrary context-free languages. What we do is we add a stack. This stack, it's a LIFO, so last in is first out, pile in French. And the stack can be of infinite size. And transitions depend, of course, on states and letters, but also on the stack. And not only on the last item of the stack, but on the entire stack. And a transition is, of course, a change of state, but it can also be a change of contents of the stack. So we can add elements or remove elements. We can stack or unstack, empiler, dépiler. And this is best understood by an example. And my example is this notorious language. It's notorious because it is not regular. Here is a push-down automaton for this language. How does it work? I have 3 states. And whenever I have a single entry state, it's 1. And whenever I get an A, I say I stay in the same state, but I also put a symbol on my stack. Whenever I have a B, I change state. I move to state 2 and then stay on state 2. And for every B, I remove an element on the stack. And this state 2 is terminal when my words ends at this state and when the stack is empty. So naturally, the stack allows me to count the number of A's so that I get the same number of B's. So when I add A's, I'm putting things on my stack. When I finished adding A's, I have part of the stack which is full, and then I'm emptying the stack. And if the number of B's is the same as the number of A's, this will be exactly the moment where my stack will be empty. And that's all. What else can happen? For example, if I add more B's than necessary, well, my stack is empty, so I will move to a different state, state number 3, and 3 is what I call the garbage state. It's a state where there is no hope anymore to obtain a word of the language, and no matter what happens here, you stay in that state, which is not a terminal one. Okay, now very quickly, before we take a break, let us return to grammars. And there is a way to display productions by using trees. It's very simple. If your rule is from S, I go to ASB, then you write the left part of the rule on top and the right part of the rule on bottom, and you draw the tree that goes from S to ASB. So it's very simple. And here to get the word AAAB with these 2 rules, I can use first the first rule to get AS, then again the first rule, and again the first rule, and finally the second rule to get a B. What is interesting with this tree, which we call the syntax tree of the word, is that the leaves of this tree are exactly the word we are looking for. Now, here the tree is binary. This is only because the rule is binary in some sense, since from 1 symbol it goes to 2 symbols. Otherwise, it's not necessarily a binary tree, as you can see here. And this works for all kinds of languages. No, sorry. This works for context-free languages because on the left, you have only 1 element. And you know that in a tree, you always have 1 father, many children. but a single file. So it's not a graph, it's a tree. And it's ordered by top bottom, the production rules, and left to right, the order of the symbols. So this is an ordered tree. Now, this slide is very important because the notation of formal grammars leads to misunderstandings. So this slide is about common errors in understanding how formal grammar works. Remember that a production will always choose a symbol. If it's a context-free grammar, a single symbol. If it's a context-enabled grammar, then it may be many symbols, but in case of context-free grammar, you choose a symbol in the word and you apply the rule to that symbol. And the rest of the word doesn't change. So one misunderstanding is sometimes we think that we apply a transformation to all symbols. No, we apply the transformation only to one symbol. So for example, if I have this word, N-A-N, and there is a rule N to A, then I will first apply this rule to either this one or that one. And then I can apply again the rule to the other one, but not simultaneously. So this is very simple, but you have really to understand it. Otherwise, you will make errors. And if you apply it, if you have two rules, one going from N to A and another from N to B, you can apply the first or the second rule to this N and either one of the two rules to the other N. It doesn't have to be the same rule. So when I'm writing A goes to N-A-N, even though I've put the same symbol on both sides, it doesn't mean that all words derived from this one will have identical left and right parts around A. All depends on the rules I will choose. And here's another caveat. There may be grammars that generate no words at all. For example, this one. This looks like a very innocent grammar, but in fact, as you can see in both rules, the S remains. So I can never get rid of that S, which is a non-terminal. And to get a word, I need to get rid of all non-terminals. A word has only terminals. So this grammar generates no word at all, not even an infinite word, because there will always be an S. If I add this rule, S sending to empty words, then I have the other extreme. Then this grammar together with this rule gives me the universal language of all words. Because you see, I can add A's and I can stop anytime. So I can produce any word. And again, this is not very interesting. So when you write production rules, don't forget to add a rule which will allow ending a word, and be careful not to be very general, because otherwise we will have much too many words. We're not going into details, but in these two slides, I give rules for the syntax of the pocket calculator. And here's an expression. You see that this expression is syntactically correct. So why do I need these rules? It's to distinguish between words which are syntactically correct and words which are not syntactically correct. And this is very important for the pocket calculator, because once a word is syntactically correct, it can calculate a value. Otherwise, it doesn't even need to start calculating, since the expression is not syntactically correct. There's an error. This is the word to. So I will finish with this slide. Those of you who are using C language may know these two tools. They are very old tools. They came with the first Unix version in the 70s. They are called Lex and Yak. Yak, which means yet another compiler. And later on, the GNU Foundation created GNU versions called Flex and Bison. These two tools allow making compilers. Lex will use regular expressions and will compile these regular expressions into finite state automata. And these finite state automata, let's use regular expressions together with a finite state automaton to choose between different kinds of regular expressions, depending on the state in which you are. It will recognize strings as belonging to some type, for example, integers, variable names, parentheses, semicolon, and so on. And it will send these types and values to Yak. Yak will receive the types, and in Yak, you describe the syntax of the programming language you want to compile. And Yak will receive, for example, a token saying command name. Value of the command name, print. When Yak sees a command name like print, it knows that it needs an argument. An argument must be delimited by parentheses in most of languages, like in C. So Yak expects command name print to be followed by parentheses. And inside the parentheses, Yak expects an argument. And this argument will be an expression. This expression can be either a variable name or a string. A string is delimited by double quotes. So all of these parts of information are sent from Lex to Yak. Lex has the dirty work of recognizing the type of the token and its value. It transmits this to Yak, and Yak sees if the order is correct. And then, depending on the order and on the values of the token, will do something with it. And this is what we call a semantic treatment. And this is how compilers are created for any language you can imagine. But of course, since we're using regular expressions and No, it's not only for regular languages, sorry. The regular expressions are just for recognizing types, and the finite state automaton I mentioned here is only on the level of lex. So if you are wondering why we need a finite state automaton, it's easy. Imagine you are reading a string. So inside the string, outside the string, when you encounter a double quote, it means string begin. Inside the string, the same character double quote means end of string. So the finite state automaton will be, whenever I read a double quote, I enter a state which is reading string. Inside that string, I'm reading characters of the string. And when inside the string, in the state, I read a double quote, I leave the state and I get to the initial state. So this is why we need finite state automata. And now we can take a break. And after the break, we will do a lab on regular expressions and finite state automata. And this will allow you to better understand these notions by practice.
Mr. Yanis, if I
Yes.
may. I've been accepted in Master 2, and it's like my first time like joining a course, because before, like, I think there was a mistake. I wasn't told like courses start before the 9th of February. Yesterday, I was on the introduction of the Masters. So, and I saw on Moodle that there were courses on the 3rd of February and then on other courses on the 2nd of February. Like,
yes.
I wasn't told that there was any courses before the 9th.
Okay.
And plus, it didn't show up on Pass. I'm fine with that. It's fine because since you recorded the courses, but there were other like classes that didn't record, and I'm not sure what I'm supposed to do. Like if somebody can give me the notes or something.
Okay, well, this may be not the place to discuss this. We will find a solution. Okay, so
I'm sorry, but I just realized when I joined, like, because you were asking stuff from the last session, and I was like, I understood everything here because we've done the same in my my university, but like I'm afraid for other courses.
Okay, but this is a personal issue of yours, which we will solve outside of this class. Okay.
Okay, thank you.
Okay. So I was saying it's time to take a break. So we will start again at 11:10. So see you at 11:10.
Excuse me, sir. I'd like to know if this course is totally online.
Yes. Voilà. Okay, so this lab is a short lab, only 1 hour, is about regular expressions and finite state automata. Why are regular expressions useful? In natural language processing, we often deal with corpora. And corpora need to be pre-processed. They need to be cleaned up, they need to be structured. And this is something which you cannot really automatize because every corpus is different. The errors may not be the same. The data may not be captured in the same way. So in this stage of processing, which is called pre-processing of your data, you often use regular expressions. This is the most important tool for cleaning up and structuring your data. Finite state automata are more machine-oriented. So often what happens is you write a regular expression and the machine will then convert it into a finite state automaton which will be easier to apply for the machine. But still, they can be useful, and we will see an example in this lab. So you can find the support of this lab on Moodle. It's about, we start with regular expressions in Python. So you need a package called RE, regular expressions, and objects, fundamental objects are regex object types, instances of regex object. The description, the representation of a regular expression is through strings. But in these strings, you must be very careful because you don't want any interpolation. So what do I mean? Imagine you have a backslash. A backslash here at this location would mean that the bracket is protected. Okay. So this is the syntax of regular expressions. But Python reads the string. And when Python reads strings, it pre-processes strings. And when you put a backslash, then you mean that Python has to process it in a specific way. And for example, if I write a \n here, then Python will read this \n and understand that I want a new line. So Python will replace it by a new line. But if it's a regular expression, I don't want it to be pre-processed. I want the backslash and the n to remain. So how can we tell Python not to pre-process strings? It's by adding this R in front of the opening double quote. So this is really essential if you want your regular expressions to look nice and to be in the regular expression syntax, use this R. Otherwise, you will have to write every backslash twice. And Python pre-processing will take the double backslash and replace it by a simple backslash. Okay, and this is really a headache. So remember R. R doesn't mean regular expression. R means row. You can use it in other cases as well, but it's really essential when dealing with regular expressions. Once you've written this, you want to communicate it to Python, and there are two ways. If you're going to use this regular expression once, then we will see some methods. And if you want to use it several times, then you can compile it. Compiling means creating the finite state automaton that corresponds to this regular expression and storing this in a regular expression object. And then you use this object. So the methods, there are many methods. These are the simplest ones. Find all for finding substrings, find iter for finding substrings and returning a Python iterator, and sub for replacing, finding and replacing. And there is also a much simpler method called match, which will find only the first match. So the difference between find all and match is that match returns only one result or none, and find all returns many results if what we are looking for is available several times. In this section, I have the nice description of the syntax in Python. syntax of regular expressions. There are still some errors. Sorry for that. I will correct it afterwards. It's because I translated the support from French to English, so some errors slipped. This is LaTeX for saying that I want typewriter font. These are greedy quantifiers and non-greedy quantifiers, always followed by a question mark. Besides 0, 1 and more times, 1 or more times, 0 once, you also have nm, so at least n times, at most m times. Here you cannot use variables, you can use only numbers and integer numbers. And of course, m has to be bigger than n. And by using simply a single number, comma, you mean n or more. Here I'm giving some explanations and also the case of the group of parentheses which is not memorized. And this is rather a reference for you. And here starts the first exercise. So our exercise will be to take this sentence, which is a French tongue twister, le bon chasseur sachant chasser, sait chasser sans son chien, and to translate it into Stimi dialect. Stimi is the French dialect from the north, in Lille, Pas-de-Calais, and so on. And in this dialect, you have only sh, only the fat s. At least for this sentence, I mean. So we want to rewrite this sentence in order to replace the S sounds by sh sounds. Here is a regular expression which will take the part of a word without an S, you see from A to R, from T to Z, followed by an S, and then the rest of the word, which can again contain S's. It will take, we will find this. Here I'm compiling this regular expression, and the compiled version of it, so the finite state automaton, is stored in R. And then I can apply method find all to R. So here I get a regular expression object with a method. What do I need? I need my input string. Here is the input string. And the result, M, is again a special class, is the class of results of a regular expression operation. And in the case of the find all method, this result is just a Python list. And this list gives me all occurrences of findings of this regular expression in the string. So to make the link between the class we had earlier this morning and this syntax, this regular expression defines a formal language. Find all will detect inside a string all the words belonging to this formal language. And these words are chasseur, which contains an S, at least one, sachant contains an S, chasser contains an S, and so on. So you see, we have only words containing at least one S. If I use find iter instead of find all, I'm getting an M, which is not a list. It is an iterator, so something I can iterate with. So what is the difference between a list and an iterator? The difference is that the list is stored in memory as a whole. So here we have only a few words, but imagine you have the whole of Wikipedia. You cannot store the whole of Wikipedia in memory. If you want to process it word by word, you should better use an iterator, and in that case, you get only one token at a time in memory. Okay? Now.
Excuse me.
Yes.
Could you just explain again what how to read the regular expression like R apostrophe A R T R T?
Okay. Okay.
Please, thank you.
Well, it's not apostrophe; it's a double quote. We could also use apostrophes. So this is a Python string.
Mm-hmm.
Adding the R means that this string is not pre-processed by Python. So backslashes are ordinary characters. Everything is ordinary character.
Okay.
Okay, now this means that here I can use strictly the regular expression syntax. I don't need to take any precautions.
Mm-hmm.
So this syntax says that when I use brackets, unprotected brackets, I get a range, an interval.
Mm-hmm.
A range, these are letters. So letters in this context, in this language, are Unicode characters. And Unicode characters have an order. And it's for the Latin alphabet, it's the order of the Latin alphabet. So when I say A-R, I mean all characters between A and R.
Okay.
If I write R-A, I get nothing because R is after A.
Okay. Oh, so the first time means every single letter except S because.
Exactly.
Okay.
Because I stop at R and I start again at T.
Okay.
And even though we are in Python, in this interval, both parts are inclusive. So I count A and R. The bracket is a single character. And inside the bracket, I give all possible choices for that character. So here my choices are between A and R and between T and Z.
Mm-hmm.
Once I leave the bracket, I get a quantifier. And the quantifier says how many times can I take characters of this kind, and the star means 0, 1, or many. So this is optional, and I can have as many as I want. Okay, so here I have letters of the Latin alphabet, lowercase letters, except S.
Okay.
0, 1, or many times. And here I have the same thing without the restriction on S. So this is an arbitrary lowercase letter, 0, 1, or many times.
Okay.
So in this regular expression, the only mandatory thing is the S. The rest can be void. Okay.
Okay, thank you.
And this you can use also in text processors like Emacs and even in what's the name of the Unix text editor? Is it simply text editor?
Liberator, I guess.
Comment?
Liberator.
No.
Why?
That's a word processor. Do not confuse text editors and word processor. A text editor displays the contents of a file without omitting anything. A word processor takes the contents of the file. In this file, there are instructions on how to present it and contents. And it will present part of the file in a specific way. So Word, Microsoft Word, or LibreOffice Writer are word processors. Here, for this kind of data, we need text editors because we want to see everything.
I'm sorry, but is Vi or Vim like a text editor here?
For example, Vim, yes, is a text editor. Vim, Emacs, and so on. These are text editors, and they have regular expressions. So you can search and replace inside them using regular expressions with the same syntax as here normally, because this is the Posix syntax. Okay. Now we have seen searching. Now with the sub method applied again to the R object, we can do replacements. Sub takes two arguments. The first one is the substitute we want, the replacement. And the second one is the string to which we applied. So why don't we see the search part? Because it's already compiled inside R. So R contains the search part, and sub contains the replace part and the string to which we applied. So since I want to obtain STIMI, my first obvious choice is to say replace all S's by CH. This is the way to obtain a fat sh in French. And what do I get? I get this. Now here, this word is okay, cherchons. But here, there's a problem because I have twice CH. We never write this twice. So here I would like to have a single CH. Okay, I will change my regular expression, and I will not search a single S, but one or many S's. So I apply the same thing again, and I get this. Le bon chercheur, cherchons, chercher, chez, chercher. Up to here, it's fine. But then here I have change. The CH is pronounced at the end of the word, and I don't want it pronounced. I want it to be mute, like it is mute here in sans. We don't pronounce the final S. So I need another rule. I need this regular expression to be applied only at word begin and inside the word, but not at word end. So how can I express this? If S is inside the word, it means that there is at least one character after it. So my regular expression has this S, one or more S, plus the rest of the word. But the rest of the word I want to keep. If I don't take precautions, this will be lost. So in my replacement, I use \1 to say, please put here the contents of the first and only pair of parentheses. So the S plus, when followed by something non-empty, would become a CH followed by the same thing. And then I get le bon chercheur, cherchons, chercher, chez, chercher, champ, champ, chien. And this is better. Now, if you watch the movie, Bienvenue chez les Ch'tis, you will find out that, in fact, in Ch'timi, the chien, the word chien is pronounced quien. But this concludes the exercise. It was only to show you how we start with something simple and then we refine our regular expression until we get exactly what we want. What is interesting with Python is that not only you can make replacements, but you can also apply functions to these replacements dynamically. Here is an example. And what I want to do is take an arbitrary string, and whenever I get a decimal number, replace this decimal number by a hexadecimal number. There is no regular expression in the world which can convert decimal to hexadecimal. This would be too complex. But there is a function, a very simple function, hex. All I need to do is define a Python function which takes an input. This input may be in string type, so I convert it into integer type, and then integer into hex, and I return the hex. So this is a very simple Python function. Écrire en hexa is the name of this function. I add this name here as an argument instead of a string, a replacement string like here. I give this argument, this name, and Python will take this string. It will search for words like this, so it will actually search only for numbers, since I'm asking for numbers. And it will replace these numbers by hexadecimal numbers, and the rest remains unchanged. Okay, so this is a case where Python is very nice for doing dynamic processing. And this is a simple example, but we could do something much more sophisticated. Go to a website, get some information, go into the database, or launch a neural network to do something. So whatever. And this can be included in the regular expression substitution mechanism. Okay, so here's our first exercise. There is a file on Moodle called Gen, so Gen like genealogy. It's a genealogy from 1551 until today of Breton people. And we're gonna read this file. It's in CSV syntax, which means comma separated values. In fact, the values are not separated by a comma, but by a semicolon. But okay, we use the same extension. And we're gonna do things with that data. Here is the syntax for reading the data. Of course, there may be packages for reading directly values in this syntax, but we will do it from scratch. And to start with, question, what does this code? Here I have a regular expression. Here I'm reading this file line by line. For each line in my file, I take this line and I apply this regular expression to it with the method find iter, so it returns an iterator. And this iterator gives me, for each result, groups. So what is this group method? Well, when you find something using your regular expression, when you find an instance of word of this language in your string, this will be group 0. And this is what we have used earlier here, or even group empty. If your regular expression has parentheses, so sub-expressions, then these will be stored into group 1, 2, 3, 4, and so on. So whenever you have selected parts of your regular expression to be memorized separately, you can access them by using group followed by the number of the ordering number of the parentheses group. So M group 1 will be this part. Now, what's the use of having only part memorized and the rest unmemorized? In fact, this works like a context. From the lines here, and there are many lines in this file, we want only those that have Paul. Where is this Paul? Now, this hat here, this is something I haven't mentioned yet, means that we want this regular expression to be applied to the beginning of a string. And the string we use here is a line of a file. So this regular expression here, without a hat, has to be applied on the beginning of each line of the file. Okay, so this is the meaning of the hat when it's not included in brackets. And we have something similar for the end. It's a dollar. If you see a dollar at the end of the regular expression, it means you have to be at the end of your input string. Okay, so here we are at line begin. We know that fields in our line are separated by semicolons. So this is the beginning of my line, it's a number. Then this is something which does not contain a semicolon. You see here the hat has a different meaning than there. Sorry, but it's not my choice. The syntax is like that. So this means complementary. So this means whatever is not a semicolon. 0, 1, or many times. So here I have the contents of a field that can even be empty. But it doesn't contain a semicolon because semicolon is the field separator. Okay? And so this is my second field, and this is the third field. So this regular expression says, in each line, the first field is a number, memorize it. Second field, I don't care about. And third field must be exactly Paul. It will keep, it will match only lines having these characteristics. And it will return only the first group, so this information. So what does this code? It finds all lines, all people in the genealogy with a given name Paul, and returns the identifiers, so these numbers for these people. So how do I know it's a given name? For that, I have to inspect the file. So I have to find this file, open it, and take a look at it.
May I ask a question?
Yes.
After the numbers, like when there's the crochet, chapeau, point virgule crochet. Why did we
Yes.
put le chapeau? I don't know how to say it in English.
The hat.
Yeah, the hat. Yeah.
Because I want the contents of this field to be arbitrary. It may contain any character. One way of saying any character is using, for example, a period. But if I take any character, it also includes the semicolon. So I want the content of a field to be any character except the semicolon, because the semicolon is my separator.
Okay, I see. Thank you.
One way of doing this is taking the first Unicode character, dash the character just before the semicolon, and then the character just after the semicolon, dash the last Unicode. But the last Unicode character is something you can't even imagine. So it's easier to use the complementary notation. So I'm saying it can be any Unicode character except the semicolon. Once you get used to it, it's really very practical.
Thank you.
So let me find that file. It's on Moodle.
If I may again, so basically here we're searching for everything that has the name Paul.
In the third position, in the third field.
Okay.
And it starts with a number. So if it doesn't start with a number, we don't want it. I will open the file and share it with you. Just a moment. Now, regular expressions deal only with syntax. So when I'm talking about fields, it's because I know these lines have a pattern. The pattern is a field separated by semicolons. And that's why I'm saying first field, second field, third field. And if I want the semantics of these fields, it's not regular expressions that give me these semantics. Regular expressions only allow me to access the data. Okay, let me share. And let me magnify a bit. Okay, hope you can read. The first line of the file gives me the semantics of the fields in French. So code, nom, family name, prénom, given name, DN, date de naissance, LN, lieu de naissance, DM, date de mariage, lieu de mariage, époux. So place and location of birth and of marriage, name of husband or wife, given name of husband or wife, date de décès, lieu de décès, so date and place of death, idem, 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 probably nothing, idem, idem, idem. So the rest is unused. So here you have very briefly semantics. And then you can look at lines. 652, Abalin Goulven. So Goulven is a given name, Abalin is a family name, and here you have the date of birth. And you see that many times date of birth is missing. In some cases, it's incomplete, like how do I find an incomplete date? Here, for example, you see here we have only the year. So this is typical of corpora where you need to clean up. Or here you see you have a blank space. Is this really necessary? No. It's parasitic, so it means cleaning up. And here you have L apostrophe in parentheses. Why? Because the name actually is Ladon, but you don't want to use this in ordering and sorting your data. So what we do now is the first step when we work with Corpora, we are looking at the data. So we get a visual perception of what the data looks like. And the code we use will find all people with the given name Paul. So my text editor has a regular expression, so I just need to copy the same regular expression to get the same result. And here is what I get. Tac. Paul Cabon, ID 2030, Paul Quat. Quat means wood in forest in Breton. Paul Guédoc, Paul Guillou, another Paul Guillou, Paul Lehir, and so on. Okay, so that's what the code does. Let me return to the support. Complete this program in order to retrieve identifiers of people born in a village whose name begins with Plou. There are many places in Brittany starting with a Plou. And we need to go further in each line until the field containing the location of birth and check whether it starts with Plou. So we will complete this expression. How many fields do we need to add? But for this, we have to inspect the data, find out how many fields to the right we will find the place of birth. And then we just write Plou as the beginning of the name of the place of birth. So you see here we have a semicolon to say that the given name must be exactly Paul, not Paul with an E, feminine, not Paul Antoine, Paul Edouard, no, just Paul. But here, since we want any place starting with Plou, it can be Plouzané, Plougastel, Plougueverne, Plouarnaud, Plouarzel. We will not put a semicolon at the end. Okay, so we don't have much time. You can do this by your own. We still have only 25 minutes, okay. I will put on Moodle the version of the support with the solutions. So for here, we just continue the regular expression until we find Plou, and we take care of not adding a semicolon after Plou so that we get all names starting with Plou. Now, next question, replace birthplaces of people with places that begin with Loc. So Plouneves becomes Locneves. Plougastel becomes Locgastel. For this, we need also an output file. So we open it, giving the name of the file and the right access. You don't need binary because this is old data, it's all in ASCII. And no accented letters, no Unicode characters, only ASCII. And here you put the string you want to write. So it normally will be linear. And in these specific cases, we will apply the sub method to linear in order to change the line. Okay, so this is also straightforward. And fourth exercise uses functions applied dynamically during substitution. And what we ask is to change the birth dates and add 10 years. Now, this seems simple. It is simple when data are well structured. But since this corpus is the original, the authentic corpus, it has incomplete data. And in that case, you need to take special care. So what happens if you have only the year, or if you have question marks and things like that? And finally, we want to do some calculations. This is, again, straightforward. We want to do something useful with the data. So here's the exercise: calculate the average age at weddings. To do this, we need to define a measure, the measure of time measurement, whether we use years or months or days. With this measure, we need to calculate the distance between wedding and birth. And this calculation can become quite complex if we take bisextile years into account. So some years have 365 days, others 366, and so on. So this can become quite complicated, and maybe, not maybe, but certainly there are Python libraries for calculating time intervals, which you can use for this kind of calculation. Now, next part of the lab is a very funny part. There is a site called regex crossword that provides you with crosswords written in regular expressions. And this is very amusing. On the site, you have different levels from beginner to expert. And of course, crosswords become more and more complex. And everything is done to distract you. So for example, here you have words with meaning. You have the word gin, node, but since it's between brackets, these are not really words. These are just sets of characters among which you will choose. Now let's try to do this one. Let me see if I can write. I guess I can write here. Okay. So here it says, I want here in this cell something which verifies both this and that regular expression. But the regular expression here is for the whole column, and this one is for the whole line. So I'm looking for this first cell. Now, this first cell, according to this regular expression, will be either an F or an A, okay, because it says that what is contained here is one or more times either Fi or A. And of course, you have three letters, so you cannot take Fi twice because you will get four letters. So it must be either Fi followed by A, or A followed by Fi, or AAA. Okay, so this can be either F or A, this cell. Now, To find out whether it's an F or an A, let me take this regular expression. It says we start with a Y or an F. Here it says either F or A. Here it says either Y or F. So we have only one possible solution, namely F. That's not very nice, but I don't know how to move it. Let me try again. F. Voila. Now, if this is an F, then this is necessarily an I, because the regular expression says I have either FIs or A's. And if this is an F and this is an I, then this one is necessarily an A, because there's no other possibility. So you see now, thanks to this level expression and that one, I have already my first column. Second column, it says it ends with a K. So this, I know already it's necessary to have a K. And, oops, sorry. And here you have either YE or OT. Is it YE or OT? If I look at this regular expression, the second character is arbitrary. So this doesn't help me. I have to look at that one. And this one says, you start with 0, 1 or many U, O, or I's. Then you have a T. And then you have at least one or more F, R, or O's. Okay. So I'm searching for an E or for a T. And here there is no E at all, but there are eventually, there is a T, a possible T. So to have those both, the only solution is to have here a T, and then necessarily I have here an O, and so on. So we don't have the time to complete it, but you see how it works. And it becomes very amusing once you are used to it. This one is a bit more difficult. And this one is also quite difficult. And then you have hexagonal ones, not only square ones. And it becomes very interesting. And as you can see here, you have all the features of regular expressions. Here, the hat to say I take the complementary, a \s is a space, question mark is a question mark, \1 is the first parenthesized expression, and so on. So you have all ingredients of regular expressions, and I invite you to use them to solve these crosswords. And don't get distracted by words like play, love, year, rice, past. These are not words. These are, we are inside brackets. So these are just characters among which you will choose. Well, so now let us switch to finite state automata. For that, and since we're using Python in this class, I found a very nice Python library for building finite state automata. It's called PySimpleAutomata. You can install it easily. Instead of using pip, I prefer using Python -m pip, because that way I can choose exactly the version of Python I want. So I want Python 3. And using this here, --user, I don't need to be root. So if it's not your machine, then this is the way to install Python packages without being root. Okay, and the documentation is there. I would show you an example. In fact, I will show you the example of this exercise. Exercise is find the conjugation of the verb parler at the indicative mode, present, future, and passé simple. So here is the result as obtained from this package. Here you see the whole automata. Now, names of states have no importance at all. I gave names S0, S1, S2, but they are really arbitrary. They just need to be unique. Here you have an incoming arrow, meaning that this is the initial state. You have only one initial state. Then every arrow is a transition, and next to the transition, I write the letter that triggers the transition. So initial state P, A, R, L. Up to now, you see it's vertical. It's a unique transition because this is the stem of the verb parler, and we stay in the same verb, so we don't change the stem. And starting from here, I have many choices. In the present, je parle, tu parles, il parle. I will have an E, parle, and this being the third person of the singular is already part of my language. My language, my formal language here is the set of conjugated forms of the verb parler at present, future, and passé simple. And therefore, this is a terminal state. If I continue with an S, I get the second person, tu parles, again a terminal state. If I continue with an N, I get something which is not part of my language, so not a terminal state, but then with a T, it becomes terminal. And I get the third person of the plural of the present, il parle, avec S. Same thing for all other forms. Now, in some cases, I can economize states. For example, here, I have passé simple, nous parlâmes, vous parlâtes. You see that these two forms differ only by the consonant T and M. Which means that once I have chosen the T or the M, I return to the same state, E, and again S terminal state. So here I am economizing some states by returning to the same. So you see that a finite state automaton does not need to be a tree. Same thing here. You see that I have parler with Z and vous parlerez again with a Z. And I'm using the same state. But I'm not doing this always. For example, here I have an S, and there I also have an S, so I could use this one, the same state here. This was just a personal choice. In the package Python simple automata, you have the possibility to minimize your automaton. So you have the possibility to complete it, to determinize it, and to minimize it. What is a complete automaton? This is something I think we forgot this morning. A complete automaton is an automaton that has all possible transitions at every state. So if your alphabet has 5 letters, then all of these letters appear as transitions for every state. Here, for example, you see I only have the P, while in my alphabet I have many more letters. So this automaton is not complete. Is it useful? It is useful because if I take a different letter here, I will get a different verb. It will not be the verb parler. Does it matter? It doesn't matter for the machine because in my other verb here, I will have no terminal states. So none of the words which I will obtain will be recognized. But still, it will be a loss of space since I will have many states which will be useless. Okay. But for a machine, it's better to have a complete automaton so that the machine knows at every step what to do when some letter arrives. So what we do most of the time to complete an automaton is we define a state which I call the garbage state. So imagine here you have a garbage bin with flies surrounding it, bad smell. And I can say for all other transitions than P, so A, comma B, comma C, and so on, I go to the garbage state. Same thing from here. All except A. Same thing here. All except R. Same thing here. All except L. And once I am in the garbage state, whatever may happen, I stay in the garbage state. And the garbage state must not be terminal. That's all. So by using this one additional state, my automaton can become complete without big expense. So it's not very expensive in number of states. I'm just adding one state. And but with the expense of many new transitions necessarily. Okay.
May I ask a question?
Yes.
About this? Only non-terminal states go to the garbage state, or even terminal ones in order to be complete?
So be careful. States do not go anywhere.
Like transition to
Transitions. Once you have a terminal state, it means that you can stop there and recognize the this path as a word in your language. But terminal doesn't mean you cannot continue. Okay, the word may be badly chosen. When we say terminal, it means terminal for words of the language. But you can always continue. And when you continue, for example, here, parla is terminal, parler with an E is terminal also. But if I continue parler with an S, I still get there. So this is okay. But if after the E, I get, for example, an X,
It's garbage. Like we
It's
put
garbage.
it. Okay. Okay.
Okay, so or Z or T or whatever.
Okay.
Well, parler with a T exists. Sorry, and this is an error. I forgot that we're only doing présent, futur, passé simple. And this is imparfait, actually. So this is an error, but I don't know how to erase it. So just forget about this. Okay, so the garbage state is something intuitive. It's just a practical way of getting a complete automaton out of an arbitrary automaton.
Thank you.
The other thing is get a deterministic automaton. So is this one deterministic? Actually, yes, because you see, we always have a single transition with a given letter. Now, this may not be very visible here, but if you write the transition table, then you will see immediately whether it is deterministic or not. And then is it minimal? No, it's not minimal. So what is a minimal automaton? It's among all the automata recognizing exactly the same language. So neither one less word, neither one more word, exactly the same words. A minimal one is the one which has a minimum number of states and transitions. And I ask this package to do the minimization. And here is what I got. So this one is so big, it wasn't even possible to display it on a single page. Let me turn the page so you don't need to turn your heads. Voila. So this is the left part of it. And then I have another 4 pages. So this one is complete, deterministic, and minimal. If you count the number of states, indeed, there are less states than in the original one. But it has become much more complex visually. And this is where it's more interesting for the machine and less interesting for the human. But again, you may find a better way of displaying it and make some sense out of it. But it's typically the kind of structures where they can be improved, but what they get as improvement for the machine is making it less readable by a human. Voila, and let me show you the code and then we can stop for lunch. The code in Python simple automata. Here it is. Again, I will magnify it a bit. Voila. So it's very, very simple. You define an automaton as a dictionary with 1, 2, 3, 4, 5 entries, alphabet, states, initial state, accepting states. So accepting means terminal transitions. You can give arbitrary names to your letters, to your states, and so on. And then transitions is again a dictionary where the entries are tuples. So this is a very important Python feature, is the fact that you have tuples and lists. A tuple can be the key of a dictionary entry. And we are using this feature here. The keys of a dictionary are pairs, And each pair has a state and a letter. And the value of the dictionary entry is the state we are going to, we are transiting to. And so all I had to do is to describe these transitions. So what I did, I drew the automaton on paper, and then I wrote the transitions in a much simpler way than that, and then I used a regular expression to obtain this syntax, and voila, that did work. And once I have this, I can test. So here I'm testing par le rang, and it will reply true. And then I test this par l'erreur, which doesn't exist. It will reply false. And then I take this automaton and I go through a package called GraphViz, which you need to install separately to get the image of the automaton, so the graphic representation in a format called SVG, an XML format for graphics. And then I ask the completion of the automaton. So completion stays in the same object. So it's the object automat which is completed and replaced. And then minimization produces a new object, new DFA. So DFA means deterministic finite state automaton. And then I draw this new automaton. So you see the code is very simple, and you can use it in your projects for arbitrary automata whenever needed. Okay, well, we will stop here. Once again, I have 2 questions which will appear in a few moments. So please answer them before next Tuesday, 10 o'clock. It's not midnight because it's a bit too late. Let's take 10 o'clock in the evening, 10 o'clock p.m. Again, questions are optional, but they are useful for you to think about issues, and then we can discuss your answers. And this afternoon, we will have a lab on Rasa, so a Python package for creating chatbots. So if you have no question, we can go for lunch and start again as scheduled at 1:30. Any questions? Okay, then bon appetit to everybody, and see you at 1:30.
Thank you.